Just think for a second about the leaps we've made. I mean, Jules Verne was writing about submarines, trips to the moon.
Stuff that sounded completely impossible back then.
Exactly. Wild ideas. And now we have tech that goes way beyond even that.
Yeah.
It really makes you wonder, doesn't it? What things feel impossible today but might just be normal tomorrow.
Yeah. And what's really interesting is this whole idea of impossible itself. Our sources actually lay out a pretty neat way to think about it, breaking it down into 3 classes.
Okay.
Right, so class I is stuff that's beyond us now, but, could maybe happen within a century or so.
Plausible, eventually.
Plausible, right. Then class 2, that could take thousands, maybe millions of years, if it's doable at all.
A much bigger leap.
A much bigger leap. And then class 3, that's the really wild stuff, things that might actually break the known laws of physics.
Wow, okay. And that's pretty much our mission for this deep dive, isn't it? We've got some great material here looking at these, well, seemingly impossible sci-fi technologies.
Right.
And we want to see which ones might actually have a shot, based on what we know scientifically right now.
Let's do it.
So let's kick things off with a big one from Sci-Fi. Force fields.
Ah, yes. The classic shimmering barrier. You immediately think Star Trek, right?
Totally. Deflector shields up.
But the core idea, this invisible shield, it actually has roots in some pretty fundamental science. It's kind of amazing that the language we even use for this stuff comes from Michael Faraday's work way back in 1831.
Faraday? But wasn't he the one who started out binding books?
That's him. He was figuring out the link between electricity and magnetism, and his big experiment showed that moving a magnet near a wire could make electricity flow in that wire without them touching at all.
Wow. No physical contact?
Nope. It was huge. It showed these invisible fields of force existed, things that could act across empty space. And really, as the sources point out, modern physics is pretty much built on understanding these fields.
Invisible fields doing things.
Yeah.
Sounds almost like magic. So how do we get from that to a Star Trek shield? What's the bridge?
Well, one piece of the puzzle could be something called a plasma window.
Plasma window.
Yeah. Imagine heating up a gas like crazy, so hot it becomes plasma electrons stripped away. Now, this plasma, this super hot gas, can be pushed around and shaped using magnetic and electric fields.
Okay.
So theoretically, you could shape it into a thin, see-through barrier, like the window made of pure energy, basically. It could separate, say, the inside of your spaceship from the vacuum outside.
A transparent energy shield. That's quite an image. Are there other angles, maybe using lasers or something?
Well, the sources do mention nanotechnology, which is fascinating. Think about creating new materials, maybe using advanced carbon nanotubes.
Okay.
And giving them special photochromatic properties, like those sunglasses that darken in bright light.
Right, transitions lenses?
Kind of like that, yeah. But imagine a material that reacts specifically to laser light. So it could change its structure, maybe become opaque, almost instantly when hit by a laser.
Ah, so it could potentially block or absorb a laser blast?
In theory, yeah. Absorb or deflect it. But, the big caveat is materials that do exactly that. They're still very much in the research phase. We don't have them yet.
So deflecting phaser fire might still be a ways off?
Okay.
Okay. But what about hoverboards? Back to the Future style. That feels a bit more grounded.
Well, that ties into another thing often linked with force fields in sci-fi. Magnetic levitation. Maglev.
Right.
The basic idea is simple, right? Like, poles on magnets push each other away.
Yep.
We already use that in maglev trains. Powerful magnets lift the train right off the tracks, cutting friction, allowing really high speeds.
Okay, so we have the principle. What stops us from shrinking that down for hoverboards? Is it just needing tiny, super strong magnets, or is there more to it?
That's a really good question. I mean, shrinking the magnets is a huge engineering challenge in itself, definitely. But the sources also bring up something called diamagnetism.
Diamagnetism.
Yeah, it's a property. Some materials have water, is one where they create a weak magnetic field pushing against an external magnetic field. And with magnets that are incredibly powerful, like tens of thousands of times stronger than Earth's field, scientists have actually managed to levitate small things, like frogs.
They levitated a frog.
With magnets? Yep, using diamagnetism. It's pretty wild to think about levitating living things like that. Makes you wonder.
Levitating frogs. Okay, that's horrible.
It is. And, if we ever crack room temperature superconductivity.
Materials with zero electrical resistance at normal temperatures. The dream.
Exactly. If we get that, then levitating really big things, even non-magnetic stuff, with magnets becomes a much more serious possibility.
So if we put all these ideas together, plasma windows, fancy nanotubes, magnetic levitation.
Right.
Are we actually close to a real force field?
Well, the sources suggest a single all-purpose shield, like in the movies, is probably still a long way off.
Yeah.
Might even run into fundamental physics problems. But the key idea isn't necessarily one magic barrier.
More like layers.
Exactly, maybe a combination approach. You could potentially layer different technologies, plasma windows for one threat, maybe a laser curtain, those advanced carbon nanotubes for energy blasts, perhaps some magnetic tech.
Ah,
You could simulate some properties of a force field.
okay. Not the perfect bubble, but something functional.
Potentially, yes. And based on that, the source material classifies force fields as a class I impossibility.
Meaning beyond us now, but maybe achievable in some form within a century or so.
That's the idea, a modified version, yeah.
All right, from shiny shields to
Mhm.
just vanishing. Let's talk about invisibility, another sci-fi classic. Romulan cloaking devices in Star Trek, right? Making whole ships just disappear. How close are we?
Well, true invisibility is surprisingly tricky. It really comes down to how light interacts with matter at the atomic level, and that's governed by Maxwell's equation.
Maxwell's equations, the fundamental laws for electricity, magnetism, and light, right?
Precisely. They describe how we see things, basically. And as our sources joke, trying to make Harry Potter invisible using normal methods would involve some pretty drastic and impossible changes.
Right, no simple spells here.
Mm.
But I have heard about some really cool new materials, metamaterials.
Yes, exactly. Metamaterials. These are substances that engineers design to have optical properties you just don't find in nature.
How do they do that?
By embedding tiny, tiny structures inside a material. And these structures can be built to bend electromagnetic waves, including light, in really weird ways.
Bend light. How so? More than just a lens or prism.
Oh yeah, much more sophisticated. The sources give a great example. Scientists at Duke University made a metamaterial that could bend microwaves around an object.
So the object became invisible to microwaves.
Exactly. The analogy they use is like water flowing around a boulder in a stream. The water just flows around and fills in behind it. So downstream, you wouldn't even know the boulder was there. Metamaterials aim to do that with electromagnetic waves, guide them around something, so there's no reflection, no shadow.
That's amazing. But microwaves are one thing. Visible light has much smaller wavelengths, doesn't it? That must be way harder.
It is much, much harder. Because bending visible light means you need to control waves that are hundreds of times smaller than microwaves. You're talking about manipulating things basically at the atomic scale, or close to it.
Nanotechnology territory.
Definitely. And the sources say there's a lot of research happening right now in nanotechnology, trying to create metamaterials that can bend visible light effectively.
So if they manage it, a real invisibility cloak. The idea is just to make light flow around whatever's inside?
That's the core concept, yeah. Light hits the cloak, flows around the person or object inside, and then carries on as if nothing was there. One tricky bit they mention is figuring out how to let just a tiny bit of light get to the person inside so they can still see out.
Right, you don't want to be blind inside your invisibility cloak. It's almost like a stealth plane, but for visible light, too. Kind of a scary thought, actually.
It is. And that nanotechnology connection is key. Being able to build things precisely, atom by atom almost, is probably what's needed for true visible light invisibility. The sources seem pretty optimistic that some kind of invisibility shield could happen in the next few decades.
Okay.
The big idea here is fundamentally changing how light interacts with stuff, not just blocking or reflecting, but guiding it. And that leads them to classify invisibility as a class I as well.
Class I again. Interesting. Okay, so we've covered making things vanish. Now for the opposite extreme. Making things, well, cease to exist. On a huge scale. Death Stars.
Yeah.
Are those planet-killing weapons from Star Wars even physically possible?
That's a very big question. You're talking about immense amounts of energy. But yes, our sources point to a couple of existing technologies that, theoretically at least, could deliver that kind of power.
Really? Like what?
Well, first, there's nuclear fusion. That's the process powering the sun, and also hydrogen bombs.
Right, slamming atoms together to release energy. We're trying to harness that for clean power, aren't we? With projects like ITER.
Exactly. In labs, they use powerful lasers to crush tiny fuel pellets, laser-induced fusion. The huge challenge, as someone famously put it, is putting the sun in a box, getting a controlled, sustained reaction going. ITER is a big international push towards making fusion power practical.
But fusion power plants, even if we get them working perfectly, they wouldn't blow up a planet, would they?
No, not based on current reactor ideas. For that kind of energy, the sources mention another possibility, also based on existing nuclear tech: nuclear-pumped X-ray lasers.
Nuclear-pumped X-ray lasers, what does that mean?
The idea is you take the enormous energy from a hydrogen bomb detonating,
Okay.
and you use it to power an incredibly intense laser beam, but in the X-ray part of the spectrum. They'd use things like copper rods, which get vaporized by the bomb's energy and are forced to laze, focusing that energy.
So you use one nuke to power an even more focused energy weapon. That sounds terrifying.
It is. There was actually a test called Cobra back in 1983, and that test apparently influenced President Reagan's Star Wars initiative, the missile defense idea.
Wow.
Now, it turned out to be impractical for missile defense because, well, the bomb destroys the laser setup when it goes off. It's a one-shot weapon.
Oh, okay.
But the principle is there, focusing nuclear energy into a beam. And the sources make a sobering point. There's no theoretical limit to how powerful you can make a hydrogen bomb. You can just keep adding stages.
You could just stack them, build bigger and bigger bombs indefinitely.
That's
deeply unsettling.
It really is. The sources even bring up an old Arthur Conan Doyle story, The Disintegration Machine, about the ethics of a weapon that could just wipe out cities. So the conclusion is pretty stark. Planet-destroying weapons, while hopefully never built, are actually theoretically possible with the nuclear technology we already have. The barriers are practical and, more importantly, ethical, not strictly physics.
Okay, wow. From blowing up planets to personal transport. A very different kind. Let's talk teleportation. Star Trek again. Beam me up, Scotty. Seems so easy. Is that just pure fantasy, or is there any science behind it?
Well, if you stick to classical physics, Isaac Newton's world, yeah, totally impossible.
Why is that?
Because Newton saw matter as solid things. Objects. They can't just disappear here and instantly reappear over there. Doesn't work like that in his physics.
But then quantum mechanics came along and messed everything up.
Yeah.
Made things weirder.
It really did. Quantum theory showed that down at the subatomic level, particles aren't just little balls. They can act like waves, and they can do these quantum leaps.
Quantum leaps?
Yeah, like jumping between energy levels without actually traveling through the space in between. So at that tiny, tiny scale, teleportation isn't completely ruled out by the laws of physics.
Okay, tiny scale seems key there. I'm guessing my coffee cup isn't going to spontaneously quantum leap across the room anytime soon.
You'd be waiting a very long time. The odds of something macroscopic, like a cup or a person teleporting just due to random quantum effects, it's practically zero, even over the age of the universe.
Right, so not that way. Is there another angle?
There is. It's still incredibly hard, but more promising. It involves a quantum phenomenon called entanglement.
Entanglement?
Yeah.
That's the spooky action at a distance thing Einstein hated, right? Where two particles are linked?
That's the one. You get two particles linked or coherent, and they stay connected no matter how far apart they get. They're tied together by this invisible, you can call it a Schrödinger wave.
Okay.
And if you measure something about one particle, its spin, say the other particle instantly reflects that measurement, even if it's light years away.
Instantly. Faster than light.
It seems that way, though you can't use it to send information faster than light. That's a whole other discussion.
Yep.
But Einstein, Podolsky, and Rosen came up with the EPR thought experiment to show how absurd they thought this was.
But it turned out to be real.
Exactly. And ironically, their attempt to disprove it actually helped us understand entanglement better.
So how does this spooky link help with teleportation?
Well, scientists have actually done quantum teleportation in labs. Starting in the late 90s, places like Innsbruck, Caltech, University of Vienna, they successfully teleported the quantum state of photons, particles of light.
Teleported the state.
Right.
Not the photon itself.
Right. They destroy the original photon in the process of measuring it, but they transfer its exact quantum information onto another photon somewhere else, using an entangled pair as a channel. More recently, there's a newer method using something called Bose-Einstein condensates, or BECs.
BECs remind me.
You cool atoms down to almost absolute zero, and they stop acting like individual atoms. They kind of merge into one giant quantum state, like a superatom.
Whoa.
And this lets us see quantum effects on a more manageable scale. With BECs, they can basically turn a beam of these supercooled atoms into a light beam carrying all the quantum info, send that light beam somewhere else, and use it to recreate the original matter beam in another BEC.
So you're moving the information that defines the atoms, not the atoms themselves.
Precisely. It's about transferring the quantum blueprint, essentially.
That's still mind-bending, but it feels like a step.
Yeah.
So what's the timeline? When can I beam across town?
Don't sell your car just yet. The sources think teleporting complex molecules, maybe DNA, maybe a virus, that might be possible in the next few decades.
Okay, decades for viruses. What about people?
That's the class 2 impossibility. The challenge is just staggering. Think about a person, trillions and trillions of atoms, keeping them all in perfect quantum sync or coherent while you scan them and transmit the data. It's unbelievably complex.
So centuries away, if it's even possible at all.
That seems to be the consensus, yeah. Many centuries, maybe never. It's a monumental hurdle.
But solving that coherence problem,
Yeah.
that sounds like it might help with other things too, like quantum computers.
Absolutely. Keeping quantum states stable in large systems, that's a huge bottleneck for quantum computing too. So yeah, breakthroughs in controlling coherence could unlock progress in both areas. But for now, beaming Captain Kirk anywhere remains firmly class 2, maybe possible way, way down the line, but facing just immense technical problems today.
Wow. Well, this has been just an amazing trip through the land of the impossible, or maybe the not yet possible, from force fields and invisibility.
To Death Stars and teleportation, yeah.
It really makes you think, doesn't it?
It really does. And it's a great reminder, like that Sir William Osler quote the sources mention. Something like, the philosophies of one age become the absurdities of the next.
And the foolishness of yesterday has become the wisdom of tomorrow.
Yeah.
It means what seems utterly impossible now.
Might just be waiting for the right discovery, the right shift in understanding or technology. Our idea of impossible keeps changing.
So, maybe something for you listening to think about. Which of these impossibilities grabs you the most? Force fields, invisibility, teleportation, and what breakthroughs do you think we need to actually make them real? The edge of what we think is possible, it's always moving, and the future could hold some truly mind-blowing surprises.